Okay, so I wanted to cover this before the midterm. I didn't get a chance to quite do it. And that is having to do with something called optional arguments or default arguments. So basically what happens is this is a kind of way of overloading a method. Because what you're doing, you're saying, so let's take a look over here. So this part right here is just, this is just the header for some class called 3D point. So 3D point is going to have what? An x and a y and a z. So we're going to have an x, we're going to have a y, we're going to have a z coordinate. And since the class is called 3D point, and 3D point is in a public area, then this is the constructor. But it's not the definition of the constructor, it's the declaration of the constructor. And inside the declaration I have int x equals 0, int y equals 0, int z equals 0. Actually, as you recall, I don't even have to have the formal name here. I could just have int equals 0, int equals 0, int equals 0. What it means is that these parameters, if they're not supplied, will automatically be initialized to 0. So now, when I go to the implementation of the same method, which is the constructor method for this class, notice I have int x, int y, int z. And then I say, this pointer x equals x, pointer y equals y, pointer z equals z. Does everybody understand why I use the pointer here? Do I have to? That's a good question. Do I have to? Not really. But I did. Okay. So I don't have to. Now, but I cannot say x is equal to x. Why?
Because that's ambiguous?
Because, no, it's not ambiguous. Because if you said x is equal to x, this is more locally defined than the property. So this is this overrides the meaning of x. So you cannot say x is equal to x, because x implies what? X implies this thing. So you're saying this thing is equal to itself. So you're not really assigning anything to the property. That's why we're using this pointer x to do a member selection. Does that make sense? Well, if I didn't use this pointer, how would I have to write the code?
Do you have to use a different name for the variable?
I could use a different name for the variable. So if I said, for example, x1, y1, z1, I could have had then x is equal to x1, like that. Or I could use star this, dot. And the reason we use pointer, because this is a pointer. This is not a reference to the host object. It is a pointer to the host object. Okay. So now, in the code that I'm using this class, I'm going to have 3 point, P1, P2, P3, P4. I am actually creating 4 objects. This one is using the int constructor, int, and then default constructor. But I only have one constructor, yes, but when I call P1, that's a constructor with no values given. Well, since I did not define a default constructor, but I did define a constructor with 3 default parameters, then automatically in P1, we default the value of x to 0, y to 0, z to 0, and therefore 0 is being assigned to the host P1 x coordinate, 0 and 0. Does that make sense? Okay. Now, P2, I send an int. Now, is this 4 going in for x, or is it going in for z? What do you think?
X.
It goes in for x. So the values of the x, y, z for P2 will be 4, 0, 0. The value here will be 5, 2, 0, and this will be 6, 8, 2. So in a sense, I've created, by having these default parameters, I've created how many constructors in one? 4. So 4 constructors are created. It's the default constructor and 3 other constructors. That's it. And you can do this default parameter stuff for any method or any constructor in any class. It gives us flexibility. Okay, so this, I think we would have seen that. So I'm going to skip through here. Okay, we did type defs a little bit. This is kind of where we stopped here, so let's just take a look at this a little bit. There's a few important things that I want to cover here. This class, it's not so important, but I'll show you a little bit of how it's kind of like a little data structure. CIRBUF stands for circular buffer. So you can think of an array. So the array starts, and rather than going from start to end, it goes from start, and then it ends at the beginning. So what we want to do is we want the pointers. As you know, like in a circular buffer, this is the front of the, if you want to think of it as the front of the queue, and this is the end of the queue, and you keep adding to the end of the queue, and you keep removing from the front of the queue. But if you run out of places at the end, and you still have some places at the beginning, then you can add something here. So the front is here, and then it wraps around it. So as long as we have empty spaces, the pointers in the circular buffer are going to go from front to rear, and then they're going to wrap around. Okay. So in this case, we're creating a circular buffer, and I'm creating an enum enumeration, which is a public enum. D size, I guess is dimension size, equals to 16. And I'm using circular buffer, and I'm saying int size equals to D size. So I'm creating an overloaded default parameter constructor. So I actually have a default constructor, which will assume to be 16 if you don't give me anything. Or if you give me something, then you can override that 16 with whatever you want in terms of an int value. I also have another keyword here called explicit. Does anybody have an idea what explicit means in C++? Explicit. Okay, that's a good question. What is explicit? And specifically, explicit is a qualifier that we can put in front of constructors. What does it mean, explicit? Sometimes, I'll give you an example. Somebody left me some pens so I can do something like this. So let's say I have a rational object, okay? So let's say I have a rational R, and I'm going to construct it equal to 3/4. Then I'm going to have another default constructed rational, S. And then I'm going to have int, let's say, int, let's say, k equal to 3. And let's say I write the following code. I write the code like this. I say S is equal to R plus K. So logically speaking, it's very clear what I'm trying to do. I'm trying to take my rational 3/4, add 3 to it, and come out with a rational sum. However, this would require, from what we've done before, to overload which operator? The plus operator for which type? In order for this to work, in the past, we overloaded the plus operator for which parameter type?
Rational.
No, we're overloading it for, forget about this. Just look at the R plus K. So this is the host. This is the overloaded operator. What type is this? Int. So we overloaded plus to take an int. Does that make sense? Okay. So clearly, if I overloaded the plus operator to take an int, I can easily construct this code, right? Easily. But suppose I didn't overload the plus operator to work with ints. Could it still work? And the answer is Yes, it could still work. And how could it work? Well, suppose I had a constructor in the rational class that looked like this. Rational, and I'm going to have here int, let's say v for value, and then I'm going to have top v. You understand what I'm doing here, right? So I'm, remember, initializing it, comma, bottom, 1. And then I don't do anything in the body, but I don't have to do anything in the body. So this is an int constructor in the rational class. So if you say, for example, rational, someplace in the code, rational x 3, then it's going to automatically call this constructor. It's going to send 3 to the top of this host and a 1 to the bottom. Makes sense, right? So I'm defining a constructor for an int parameter to construct a rational. But at the same time, if you think about it, I'm kind of defining how to convert an int into a rational. How to build a rational out of an int is equivalent of how to convert the int into a rational. Right? So therefore, when the compiler sees this, and of course I'm not going to go bother doing the parse tree, but you understand that's a very simple parse tree. When the compiler is interested in this code, it says, I have a rational plus an int. And it looks for an overloaded plus operator that takes an int. It doesn't find one. So it looks for the next best match. And the next best match is, do I know how to build a rational out of a int? And if you have this constructor, the answer is yes, you do. So therefore, what the compiler will do, it will implicitly, what does that mean, implicitly? Without being asked. Without being asked. What do you mean without being asked? You're not constructing anything. Do you see a constructor here? No. So the compiler will implicitly, without being asked, make a constructor call to a rational for k, and it will then call the rational overloaded plus operator for rationals. Because we did define that one. Remember that? We were able to take r plus s, where s is another rational. So therefore, this is the parameter rational. This is the host rational. But here, this is an implicit call to the constructor. Okay. All right, now, so why am I talking about that? The reason I'm talking about that is because here, I put a special word here. This is the opposite of implicit, which is explicit. When somebody explicitly asks you to do something, what does that mean? They ask you to do it. Do the dishes. Okay, that's explicit, right? There's no question about what I'm asking him. I'm asking him to do the dishes. Okay, but implicitly, maybe I stack the dishes up very, very high until he gets to say, oh, maybe I should do the dishes. I never asked him, but he gets the message. It's implicit, right? I'm not saying it, but he knows what I want. So that's the difference. Now, so when you put explicit in front of a constructor, and only constructors get this keyword if you want to do it, it means that you're saying, do not do what I showed you over here. If you have to convert or build a circular buffer out of an int, don't do it. Don't do it. The only time I want this constructor to be invoked is when I invoke it. Do not use it to automatically convert ints into circular buffers. Does that make sense? And so, now that makes a lot of sense, and I'll tell you why it makes sense. Because basically, when I say that I want to do when I want to construct a circular buffer, this d size, this int value, is the size of the buffer. How many locations are you going to give me? That's what this d size means. It doesn't mean that it's an equivalent to an integer. Whereas you can think in our example underneath here is when I say rational 3, that's equivalent to rational 3 over 1. That is equivalent to a rational. the integer 3 is equivalent to 3 over 1 rational. But the circular buffer 16 is not equivalent to a circular buffer. So we want this constructor to be used only as a constructor when it's explicitly, specifically called, and not automatically by the smart compiler, trying to make things work for me. Okay, good enough. Okay, so now what we have is we have a method called produce and consume. Since it's the circular buffer and the elements are going to be of some type, so what we're going to do is we're going to, by produce means we're going to put another character into the buffer. And consume, we're going to remove a character from the buffer. Notice that I am removing a character by consume and adding a character to the buffer by produce. This is what I'm adding into the buffer. This is what I'm returning. Notice that I'm returning an int. Well, why am I returning an int? Because I can. Because an int is basically just a larger integer type than a char. Char is going to be 8 bytes, and an int is going to be 16 or 32 bytes. Well, they're both integral types, so therefore the only thing different between a character is that it's going to have 8 bits, whereas an int might have 32 bits, where the first 24 will be zeros. No harm done. I can do it. Okay. Is empty is a Boolean. Notice that I'm coding this. Notice that the code is directly here. Right? So this is the header, but yet I'm coding the method. Can I do that? Absolutely. Now, does that mean anything that I'm coding it here versus coding it there? Does it make a difference where I code the method? And the answer is yes, it does. When you code the method in the header, the method becomes known as what we call an inline method. Inline method. When you code it in the header, it's an inline method. And I'll be very clear about what inline means. So you can see is empty is an inline method, is full is an inline method. Notice that produce, consume, and the constructor are not inline. Okay. I don't think the constructor is going to go inline anyway. And then what is this thing over here?
Constructor.
So this is a destructor. What's a destructor? It's the opposite of a constructor. Whereas a constructor creates an object, the destructor, which is the same name as the class with a tilde in front of it, it's always tilde class name, is a destructor. Now, normally we get a destructor which basically does nothing. Always. But sometimes we want our destructor to do specific things. In this case, because, look over here. You see what CB is? What is that? It's a pointer to the buffer. So CB is a pointer to the buffer. This is the pointer to the buffer. This is the buffer. So now, depending upon how big you want the buffer, that buffer is going to point to different length buffers. Could be 16, could be 16,000. Okay? So therefore, the buffer is not allocated at the construction time automatically, AUTO, automatically, but it's allocated actually dynamically from the heap. Because the constructor at runtime, we have to say, how many do you want? I want 16,000. I want 100,000 buffer. Okay. So now I have to call the new operator and do that, but that's coming from the heap. Which means that when we destroy the object, if we don't return that buffer back into the heap, we're going to have a memory leak, the size of the buffer that we just allocated and did not deallocate. Okay. So that's why we have a specific destructor here. Head is going to be the index of the first character in the buffer. Tail is going to be the first empty slot in the buffer. So if we have, here's the first one, here's the second one. So let's say we put the first one into the tail. Now we're going to move the tail here. And here's the head. So the head is pointing at the first character, and this is the empty one. Next time we add, we're going to add here. So tail is going to go over here. And if we put another one, tail's going to go over here. If we remove one, the head's going to go over here. So the head will go from 0 to 1. 0 to 1. Size is the capacity of the buffer, easy enough. CB is the pointer to the buffer, which will allocate. And then we have an INCR increment is a function that's going to be wrapping our indexes around. So the index will go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, n minus 1, 0, 1, 2, 3. So as you increment it, it's always going to increase it by 1, unless it's unless it's at the max. If it's at the max, increment will send it back to 0. So let's take a look at the code for some of these functions. So you can see over here, this is going to be our circular buffer constructor. Notice that I am commenting here equals d size. And the reason I'm commenting here, because you cannot do this here. The default parameter has to go in the header. You don't do it in the header and do it here. Why? Because, God forbid, you make a mistake, then you're going to be really messed up. What is the compiler going to do? It's going to give you one size or the other size. So you only put so I put it here as a reminder to myself that there's a default parameter of d size in here. Now, so in the constructor, all we do is we initialize the head and the tail and the length to 0. Size is equal to s, that's what I want. And then I initialize the buffer to s. So the buffer goes to the size of length s, and the head and the tail go to the 0 location. This is the circular buffer destructor. Why do I have to have this? What if I said delete CB? What would happen? What's CB? CB is a pointer to? Pointer to? Type. Pointer to? Pointer to? Pointer to char. Okay, so therefore if I simply said delete CB, I would return only one character, 8 bits. Okay, but what I want to do is I want to return the buffer that CB is pointing to. So that's the syntax C++ requires. So now, when is the destructor called?
At the end of the
When is the destructor called?
end of the program.
That's a good question. End of the program? Yeah. But when is it called during the program? Well, first of all, the object is a circular buffer. You know when the constructor is called. The constructor is explicit. When I call it, that's when it gets called. But when does the destructor get called? We never call the destructor. Any guesses? When does the circular buffer destructor get called?
Garbage collection?
No garbage collection in C++. But that's a great guess. They didn't come up with that idea yet. So the answer is, it gets called when the circular buff object goes out of scope. So if I have a method, and inside this, and this method could be main, or this method could be f or g or something else or some other method. So if I have a method, and inside this method I have a circular buffer, then that circular buffer probably is automatic, right? So as I enter the method, circular buffer is created. And the constructor then dynamically allocates a heap allocated buffer. Okay. So now I'm proceeding through the method. Eventually maybe I go places, go places. Eventually I come back here and I finish this method. When this method goes out, what happens to automatic variables? They get deallocated. When they get deallocated, then automatic variables call their destructors. Does that make sense? So if circular buffer is allocated automatically, the destructor is called automatically on function exit. Now, there's another possibility. If I create in my code, if I have a pointer to a circular buffer, then that's not a circular buffer, that's just a pointer, right? So if I said circular buffer pointer equals new circular buffer, 16, 100,000, whatever, then what am I doing? I'm dynamically creating the circular buffer, not automatically, but I'm dynamically creating it from the heap. Which means the circular buffer is not going to automatically disappear. So therefore what I have to do is I have to delete the pointer to the circular buffer. And when I do that, that's going to trigger the destructor in this case. Does that make sense? Yeah? I mean, I don't think it's complicated. It can't happen in either. So you either create a circular buffer automatically, in which case the destructor is called automatically, on function exit, or block exit, whatever is appropriate, or you allocated the circular buffer dynamically. If you allocate it dynamically, then it's not going to go out of scope. Then you have to delete it. And when you delete it, that triggers the destructor. Okay, good. All right, so that's fine. And so you can see the destructor here. And that's what destructor does. You don't call the destructor. Well, you can, when an object goes out of scope, that implicitly calls the destructor. And when you delete a dynamically allocated circular buffer, that implicitly calls the destructor. No garbage collection. Okay, so now here, let's take a look at this simple functions here. Simple functions, do we have, full we already have, I think, right? We covered those. Those are the inline functions. So notice here, return length is equal to 0. Length is equal to 0. How many do you have in the buffer? If the condition is length is equal to 0, then we'll return true. Full is return length is equal to size. So if you have 16, and it's supposed to be 16, you have 16, that's full. So that's pretty easy. And basically, sorry about that. Sorry about that again. Okay, I'm really losing my mind here. Okay, here we go. So now let's say, now we're going to produce. So if we want to produce a character into the buffer, first we check if is full. Can I say this pointer is full, or do I have to say is full? Could I say this pointer is full?
No.
Yeah. Do I have to? No. So if I am full, if the circular buffer is full, then we do a standard error, produce buffer is full, new line, return -1. Otherwise, it's not full. Put the character into the tail of the buffer, increase the length, and increment the tail, and return 0. What does 0 mean for us? All good. So we're going to use 0 means good. What about consume? Consume is if it's empty and you want to consume, then error, consume buffer empty, return -1. But if it's not empty, then take the character C out of the head of the buffer, decrease the length, and increment the head, and return C. Okay? Do we have the... here, okay. Now I do have the increment function here. So the increment function, notice that it takes x. It's a private method. I made it private, which means I don't want other people to increment the counter, because the counter is kind of a private thing. Okay? So I made it private. And I'm taking x. Why is it x? Why do I need a parameter? Because sometimes I'm incrementing the head, and sometimes I'm incrementing the tail. So because I actually want to change the actual parameter, I have to take them by reference. That's why I'm taking them by reference. If I didn't put a reference here, it would be a real problem, because I'd be getting a copy of the head and incrementing that, but the actual head was still here. So next time I went to consume, I would consume the same thing again. That would be a problem. So you can see why it's absolutely necessary to take this by reference. And then I'm going to say if plus x equal to size. Now remember, if my buffer size is 16, my indexes are from 0 to 15. So suppose it's 14. If x is 14, what's plus x? 15. Is 15 equal to 16? No. So therefore, we don't do this, we're done. So 14 goes to 15. Next time I increment x value is 15, what's plus 15?
16.
It's 16. Therefore, since the condition is true, x, instead of going to 16, goes to, instead of going off the buffer, it goes back to 0. That's the circular nature of it. That's it. Okay, so nothing fancy here. We talked about casting already. Arrays and pointers. We can talk a little bit about this. All right. let's look at this class. So this is another simple class example. Class is called vector 2D or two-dimensional vector. So we have, what kind of constructor is this? Default constructor. Is it inline? Yeah, why? Because I'm coding it, right? All right, what about this one? This is a float constructor, also defined in the header, okay? I'll talk about inline in a little bit more detail in a second. And then I'm going to have a difference. So if I want a difference, basically, I want to take a vector host and a vector parameter, which I'm taking by reference, and I'm returning a vector. So I'm doing a difference of vectors. Then I can have an inner product. For inner product, I'm coding that method in line. So the inner product is going to multiply x. What's x? X is my float, right? By parameter x plus host y times parameter y. I'm going to multiply those two, and I'm going to return that as the inner product. Then I'm going to have another method which is not in line. It's going to be defined outside. It's called is parallel, to find out if two vectors are parallel to each other. Then I can have another one, this one I actually do inline. There's a mistake here. This should not have a semicolon here because I'm coding it. Okay, so this is actually a inline method. And I'm returning the non-zero value of the host, logically and parameter non-zero. And the absolute value of the inner has to be less than some very, very small threshold. We're allowing for real numbers to be a little bit imperfect. So as long as the absolute value of the inner product is going to be less than some 1 billionth or something like that, some delta, then we're going to return yes. Non-zero simply says if it basically return the condition of x not equal to 0 or y not equal to 0. So if either one is not equal to 0 or both, then it is true. Displays a display method and float parameter properties. So you can see over here, I can write the code like this. So I create an array of ints, 1, 2, 3, 4. I have a pointer, AP, is equal to the address of m sub 3. What type is m sub 3? What type is m sub 3? Int. What type is ampersand m sub 3? In pointer. It's an in pointer, right? It's an in pointer. So therefore, I can assign it to an in pointer. So I'm initializing AP to the address of, in this case, this element, right? Which is sub 0, sub 1, sub 2, sub 3. Okay, I is equal to. Now that I'm creating a vector 2D pointer v. So v is a pointer to a vector, new vector size 2. And I'm going to assign the value of v0 and the value of v1. And then v2 pointer vp is going to be address of v1. So this is a vector pointer. Address of v1 is going to be, address of v1 is going to be the address of the second vector in this array of vectors. And then I'm just going to test some values out using these references and pointers. So nothing too impressive here. Let's see if we want to do anything here. All right. Let's sort of finish up the idea of arrays and pointers. Before I do that, let me come back to inline functions so that we understand what they are. What is the advantage of making multiple methods, of breaking the responsibilities of a class into multiple methods? What's the advantage of that? Reusability, right? Right. Also, each method has a what? It's a very what? Very? But it's very what? Focused. It's very specific. Generally speaking, you want a function to do one thing. Not 5 different things, but you want a function to do one thing. That's the goal. So the idea of taking a responsibility of a class and breaking it up into, for example, 5 or 6 or 8 methods is that each method has a purpose, has a single purpose. And 8 of them have 8 single purposes, and all those purposes together make up the responsibility of the class. Does that make sense? So that's what's good about it. I'm looking at the slide. It's not telling me what I'm going with. Now, and so the advantage of methods is that allows us to break up responsibilities into focused, coherent pieces of logic. Okay. What's the disadvantage of having many methods? What? There's a disadvantage. What's the disadvantage of having many methods? Think about it. Think about. Okay, I'll give you a hint.
Memory.
What's going on?
It takes a long time to process
Why?
because it has to go through all the methods every time you call one method.
Okay, so you're on the right track. So basically, the downside of having a lot of different methods, is that you have what we call method call overhead. What is method call overhead? It's the stack. It's the putting the method on the stack. It's the putting next one on the stack. It's removing from the stack. It's restoring the instruction. Remember, function is in memory. Here, another function is here, another function is here. So if this is F, G, and H, and F is all of a sudden going to call G, then the next instruction is going to be here. But when I return from G, I have to have a note in the stack that says when you come back to F, you got to be here. That's where you popping back into. So I got to keep track of where I exited from main to get to F, where I exited from F to get to G, where I exited from G to get to H. When I come back from H, I have to then restore the instruction pointer in the CPU back to H. When I exit from H, I have to restore the instruction pointer back to G, back to F, back to main. Not to mention, take off the parameters that have been passed back and forth. Function call overhead is the time that it takes to switch the function and the local environment of one function into another function. So, how do you get around functional call overhead? We like having functions be focused and single purpose and coherent. We like that. It's a good design. It's the best practice to have a function have a single purpose, to be well defined and not ambiguous and not all things. The answer is, I want the advantage of calling a function, but I want to remove the function call overhead. And the answer to that question, the answer to that riddle is inline function. So what the heck is an inline function? So what happens is when a function is labeled inline, the compiler becomes really, really smart. And what it does is, so imagine now that this is the code for the function f, and f is going to call g. And g is an inline function. So here is f, from here to here is f, here is the call to g. It's just a normal call to g. But the compiler knows that G was marked inline. What that means is that the compiler will go into that line, which called G, and replace it with the contents of the function G and remove the call. So that at runtime, there is no call. And here's the problem. Can you have a variable called int x in f? Can you have a variable int x in f? Yeah. Duh. Right? Of course I can. Can I have a variable int x in g? Is there any problem between the two x's? No, because when I'm in f, in that stack frame, that x is the local x. That's the active frame. That's my pointer is at the active frame. When I call g, that's the active one, and I look for that x. But now, I am in f, and I have an x that is true all the way here, and now I'm adding the code to g here, which also has an x. Do you understand the potential problem we could have here? Okay. So what happens is the compiler has to be smart. The compiler renames all of the local variables in the inline function it changes their name. So they are uniquely different. So even if there's an x and an x, this x becomes renamed. Something like g dot x, or g underscore x, where g is the name of the function that it's inlining. Does that make sense? So that's the process. So why not make everything inline? I mean, hello? No function call overhead. There's a problem to that. There's a problem with that because if you have a large program and you have a large function and you make that function inline and that function is called 100 times in the program, you're going to replicate the size of the code by 100 times the size of that inline function. That's not good. That's not good because what it's going to do is going to slow the program down because now the program is requiring more memory, so there's going to be more swapping out of memory, out of paging out of the operating system with the memory that's allowed for this program. So you don't want to make everything inline. What's the good rule of thumb? The good rule of thumb is 1 or 2 lines max is a good candidate for an inline function. If it's a longer function than that, it's typically not a good idea to have it inline. Notice that the code that I had previously, I don't know what, the code that I had previously on the system. We had, oh yeah, so over here, notice that my inline function is return length equals 0. That doesn't take up any more room than the actual call. Very small inline, very small inline. Okay. Is this the only way you can create inline functions? And the answer is no. There's a keyword in C++ called inline. So for example, let's say I wanted to have the consume function, which is not a good idea because it's not 1 or 2 lines. If I wanted the consume function to be inline, all I need to, but I didn't want to code it here. How come? Why wouldn't I want to code it here?
It's not one line.
It's not one line. It's going to just look like a mess. It's going to look, my header look silly. And also, I want to hide the implementation. I want to hide the implementation. So I want to code it in CPP, but I want it to run inline. Even this one, let's say I don't want anybody to know length equal to 0 means that it's empty. I want to hide it. So what you do in that case is in front of consume, you would say inline int consume semicolon. You'd make the header tag it with an inline keyword. Then, when you go to implement it, which one was consume, right? I implement it exactly like this. I don't have to put inline again. Because the inline is part of the header. The header says you're inline. The header says you're an optional parameter. The header says you're a friend. Header has all its stuff in there. So once you implement consume, if you tag consume as inline, it is inline in the code. And again, not a good idea here because you can see that it has multiple lines. Okay, let's jump forward here. Arrays and pointers, so we talked a little bit about that. So let's look at this definition here. What is A? Well, array is a very general answer, but yes, technically you're not wrong. So A is a pointer. It's an array of arrays of int. What's an array of int? It's a pointer to int. What's an array of an array of int? It's a pointer. So it's a pointer to an array of int. So it's a pointer to int. Type. Star value of A? 2. Yeah. Okay. So now, notice that, what does 4 mean? So this means this is the first array, right? And so this is what? This is the first element of the array. And that is also an array. So this is A sub, this is A sub 0. This is A sub 1. This is A sub 2. How many elements does A have? 3. 3. A sub 0, A sub 1, A sub 2. Has 3 elements. It has 3 elements. How big is A sub 0? How many elements does A sub 0 have?
4.
4. How about A sub 1? 4. How about A sub 2? 4. How come I said 4? Because
It's fixed.
notice that 4 is basically put in there as a dimension. How come I don't have to say A int A3, 4? Well, I'm defining it. When you define a one-dimensional array, you can say int x bracket equal parentheses or curly bracket 1, 2, 3, 3, 4, 5, 6, 7, 8, 9, 10. So I don't have to specify how many elements I have in my array. That's why there's no index here. I don't have to specify how many elements I have in my array. But I can. If I wanted to say A sub 4, 4, would it still work?
Yeah.
Yeah.
Yes, it would. It would still work. Because basically what I would be saying is that A is an array of 4 elements where each element has 4 elements in it of type int. Which means that this would have 4 ints. 4 ints. What's the value of A sub 1 sub 2? 0. Why? Because all arrays, elements that are not initialized, if any is initialized, they all initialize to 0 that are not initialized. If you initialize 1, the rest of them initialize to 0. What if you don't initialize 1? Then they don't initialize. Oh, okay. So if you initialize 1, they all initialize. Either to 0 if you don't give them anything, or to whatever you give them. So what is the value, so if I put a 4 in here, what's the value of A sub 3 sub 0? A sub 3 sub 1. A sub 3 sub 3. You understand? Chris? Does that make sense? So if I say A 4, 4, then I have 4 elements, which means I have 1, 2, 3, 4, and each of those elements is size 4. So that the last element, since it's not initialized, 0. Okay. A sub ampersand A00. 0. First of all, what type is that right side of the expression? What's ampersand A sub 00? 0? What is the type? Say again? Int pointer. Very, very good. And why is it int pointer? Because A is an int pointer pointer, so therefore twice dereference is an int, and then unreferenced or referenced again becomes a pointer. So it's an int pointer. So P is pointing at which element? At the 0. It's basically it's the value of P is the address of that 0. Okay. Now, what type is A0? No. What type is A0? And if you want to be more specific, don't get too fancy. I'm just looking for a different word. It starts with C. Const. Okay. So actually, A0 is a constant pointer. It's still an int pointer, but it's a constant pointer. Why? Because A sub 0 is basically pointing not to the 0, but it's pointing to the array, the beginning of the array, which, by the way, is the same address as ampersand A sub 00. It's the same address, but they're not the same types. Ooh. Same value, different types. Just like 0 can be null and 0 can be pure value of 0. Same value, but they have different meanings, and the program will expect them at different times and reject them at the inappropriate times. Question. What's the star value of A sub 0? Well, if you believe me that A has a star value of 2, right? So therefore A sub 0 has been dereferenced once, so therefore our star value must be 1. Perfect. Which means that I can either put a star in front of it, or I can put another bracket after it. Same thing. So I could say A sub 0 sub 2, and that makes sense. Or I can say A sub 0 plus 2 star in front of it and dereference that pointer. Okay, what type is A sub 1? Const in pointer, okay, same thing here. So Q, R, and S. So tell me what Q, R, and S are pointing at. So Q is pointing at the beginning of this array, beginning of this array, beginning of this array. Notice that S, which is S sub 2, is pointing right here, which means it has skipped those two zeros that are not initialized. But they're there, and they have to be there. If you try to write this code and skip this numerical value here, it would be an error. Because then C++ could not do pointer arithmetic on the A. It could not do pointer arithmetic on the A. Because basically A sub 0, what's A sub 0? What's A sub 1? A sub 2? And A sub 3 is here. So you have to have that so that when you add something, it knows how many elements to skip. Okay, so Q, R, and S. Now, let's take a look at this. So P plus 4 plus 1. P is pointing at what? It's pointing at the first element. The type of P is an in pointer. Plus 4, you move 4 plus another 1, 5 ints forward. So you're going to start here, 1, 2, 3, 4, 5. You're actually pointing at the 5 right now. And then dereferencing it, you get the 5. It's going to output a 5, which is A sub 1 sub 1. This is A sub 1 sub 0 sub 1. Q plus 2 times 4 plus 2. Q is what? Q is the beginning of this array. It's a pointer to this array, the beginning of the array. So Q, what type is Q? It's an in pointer. So I'm going to add to it 2 times 4 plus 2. That's going to be, so I'm starting where? I'm starting at here, right? Hold on a second. Starting here, right? Okay, so when I add 2 times 4, this is 1 times 4, this is 2 times 4, right? Plus 2. That's now the value of 10. C out star R, what does that give me?
4.
Yep. C out star R minus 2.
2.
Good, that gives me the 2 because remember, these are really contiguous. They're two-dimensional in your mind only. They're really contiguous memory. They're contiguous. No breaks. What's S sub 3, if we do that? So A sub 2, 0, 1, 2, is pointing here. So this is a pointer to this. So it's a pointer to this. It's basically pointing to this array, one-dimensional array. So S sub 3 is going to give me 11. 0, 1, 2, 3. Good. All right. Pointer arithmetic, very, very important, and we already know about this. A pointer plus integer returns a pointer. If what type is the pointer return? The same type as this one. So if it's a float pointer plus int, it's a float pointer. If it's a vector pointer plus integer, it's a vector pointer. The pointer increases by size of star pointer. Whatever you're pointing at, that's what you increase by in terms of bytes. If you're pointing at ints, and int is 4 bytes, each plus 1 is 4, 4, 4. If it's a double, maybe 8, 8, 8, like that. Okay. So therefore, if I have a vector, so here's a vector. They should have a 2 in there. I don't know why I have 2 in there. Because if I'm using 0 and 1, they have to have a 2 in here. I have to have 2 of them. So it's a basic. This is a pointer to a vector of vector 2D. I should have a 2 in here. Then vector sub 1, I construct a vector, put it in here, construct another vector, put it in here. and then vector 2D star VP, this is a vector pointer, is equal to V. And then I can say VP plus plus, what does that do? Moves the pointer from, initially the pointer was pointing at the first one, now it's pointing at the second vector. That's all. Okay. Skip this. I want to skip. Okay. So let's stick with pointer arithmetic. Valid operations: pointer plus integer. We know that. Pointer minus integer. We know that too. Pointer minus pointer. It's legal, but should be pointers in the same array. Suppose I have a pointer to a buffer, also known as an array, right? And then I start this pointer the same place, and I do plus, 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 plus. So now this pointer has offset into this array. If I do this pointer minus this pointer, what am I going to get? Pointer minus pointer returns an int. What do you think it's going to return? So look what I have here. I have an array with a buffer. I set this pointer to equal to the same as the array. Then I do plus, 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 plus. Now I do this pointer minus this pointer.
Will give you the difference?
It will be the difference, but not the difference in bytes, the difference in the number of elements between the same type of pointers. So for example, if this was a double array, then plus plus goes to 8, 8, 8, 8. This pointer minus this pointer, 4. Why 4? Because it's 4 elements of that type. So difference of pointers is an integer. You have to be very careful with that, because you could really get crazy stuff that will really mess your program up badly. So make sure, typically what you do is you fix the first pointer on the first element. Then you let the other one go do its thing. And then at some point in time, if you know this one is to the right of it, you say this minus that, and it tells you the number of elements in the array of that type. Yeah, I don't know if I need to cover that. Matrix multiplication. You guys all know how to do that, right? I need to do that. Too easy. Okay, let's look at the polynomial. So if I don't cover it, you have to read it. You can still read it. Okay, we're going to, I think on the midterm exam I had an example of this polynomial, right?
Yes.
Which is fine, because I introduced it, so I explained it clearly, so you should be able to figure it out. So, and I think what do you guys have to do, like a derivative? Okay, so polynomial, let's say we wanted to have a polynomial, and then we wanted to store this polynomial specifically. So we could store it as a one-dimensional array, where the exponent of the first term would be here, the coefficient would follow. Then we would have the exponent of the next term. Notice it was 5 power 2, coefficient, power 1, coefficient. This is a constant, so it's power 0, and coefficient. And then here, sometimes we like to have like a little terminating value. So the minus 1 means the end of the storage. So in this particular example, what we have is a polynomial. And basically, the polynomial has, notice that we have an inline constructor here. We have a int constructor. We have an overloaded plus, so we can add two polynomials together. Subtraction, multiplication of polynomials, the degree of a polynomial. What's unsigned int? It is an int where the high bit is not regarded as a sign. Allows you to go to higher values, right? And then we have a output operator, which is a friend, which is very normal, very typical, right? You've seen that before a few times. And so now, the whole polynomial, that whole buffer right here, is just an array, is essentially created by having a pointer to these ints. That's all. And I'll just show you a few of these operations. I'm not going to dwell on this, just to show you how this works. I want to show you this right here. Notice that this is the header file for the polynomial, and I have the inline tag. So I have inline int max. And I use capital letters. I probably should have used small case letters. Otherwise, it looks too dramatic. Too much like a macro. But it's legal. So what I'm saying is I want the function max to take two int parameters and return the maximum of those two values. And I want this function to be inline. So effectively, the code here will be inserted wherever this function max is called. Likewise, same thing here. You guys are familiar with this operator, right? So basically, x and y come in. X greater than y, true, return x. False, return y. Like that. Okay. Here is my polynomial construction, where I get a pointer to an array. So somebody creates an array of these coefficients and exponents and gives me the number of terms. And then what I'm going to do is I'm going to say n is equal to 2n. So n, the number of terms, I'm going to say 2n because I need to double. Because I need, for the number of terms, I need a coefficient and a power for each of them. So I need two of them. That's why I double it. And then I allocate my poly to be that doubling plus 1 for the terminator, for the minus 1. And then all I'm going to do is I'm going to go from 0 to less than n. I'm going to copy from the parameter that's passed to me directly to my array. So for example, if my constructor passed me this array, I would just copy this into my poly buffer, term for term. That's exactly what I would do. After I do those basic ones, then I'm going to put into the last location, I'm going to put in the last one, the terminator, which is the terminating symbol, which is the minus 1. Okay. I want to show you, so I'm not going to spend too much time on this, but I do want to at least look at this one right here. We're very welcome for not giving you this as a midterm problem to do, which would have been a lot harder than the derivative. This is actually the addition of polynomials. So you want to basically take a host polynomial and add to it a parameter polynomial, and you want to return the resulting polynomial. Okay? So what I'm going to do is, and I'm just going to go briefly through it so you can sort of highlight what's going on. The first thing I'm going to do is I'm going to set A equal to the buffer of the host. That's the polynomial buffer for the host. B is going to set equal to the polynomial buffer of the parameter. Okay? And I'm going to say while, what's star A? Star A is the first element of the buffer. So star A would be like the power of the host first one, right? So this means while the power in the buffer is at least a constant or higher, while the power in the other parameter is greater than or equal to this one. So I'm saying as long as I have terms, while I have terms, but the b terms are higher power, simply copy b power into c. What the heck is c? C is the temporary. That's the one I'm creating that I'm going to return. I got to return the sum of these polynomials. So I'm copying the exponent of b, bumping the pointers, and then I'm copying the coefficient. And then I check again. Hey, do I still have terms? Yes. Do I still have bigger terms? Then take another term. And I will keep taking them. So when do I drop out? Well, I drop out if I still have terms here, but I no longer have terms here. What's going to happen here now? Then that means that I have terms in this one, but I don't have bigger terms here. If I don't have bigger terms in the b polynomial, I must have terms that are less than or equal. If they are equal, I have to combine them. If they are less than, okay, then I can just take them. I don't have to combine them. So therefore, as long as there are no more bigger terms in b, I will simply go into c and take the power of a. But then I will check, because the power of a, which is not smaller, it could be equal to b. So I'll check, does b, by any chance, notice that when I took a, I didn't bump it. No plus plus here. because I want to compare. I took A into the result polynomial, but then I say, hey, is it possible that the power of A matches the power of B right now? If it does, then star C is equal to star plus plus A plus star plus plus B. What am I doing here? I already took the power. What am I doing? I added the two coefficients. Because the powers match. But then I'm going to check if C plus plus equals 0, what happened? Remember, star C is the coefficient. I didn't bump it. So star C plus plus is still star C. I'm checking if the coefficient by any chance is 0. How does that happen? When the two terms cancel out. 3x minus 3x. So if the terms cancel out, C minus equals 2. I'm backing up off that term. I'm not taking that term. Understand? Okay. All right, so you get the basic idea. And so this loop is going to continue going while A has terms. So while A has terms, I will take B's bigger terms. Eventually, B doesn't have any bigger terms, so I will take the A term, check if it's not matching with B. If it's not matching with B, then I simply will take all of A, because it doesn't have a corresponding term at all. And then I'm going to go to A plus plus, and I'm going to continue. Does A still have terms? Eventually, A will not have terms. When A no longer has terms, I'm going to go to B, and as long as B still has terms, because the power is greater than or equal to 0, I will simply take the power, the coefficient, just keep going, take them all. So I will build this C buffer, and then what I'm going to do is I'm going to create a polynomial called ANS, take my TMP, which is my pointer here, and what is the TMT? Blah, blah, blah. So TMP is here. Yeah, so TMP, notice that TMP is equal to C is equal to nu int the length of the result. So C, what's the difference between TMP and C? TMP is fixed, never moves. What happens to C? C is always moving, right? C is moving through the temporary result. So what I'm going to do is I'm going to construct the polynomial answer with the original location of the C buffer, which is TMP, and I'm going to say C minus TMP, that's pointer difference. Get it? Tells me, so C minus TMP will give me the number of what? It will give me the number of coefficients plus powers. So it'll give me double the number of terms. So I'm going to then divide it by 2. And then once I do that, then I know that my constructor is going to build its own buffer. So I delete TMP. Notice that I have an error in this code. What's wrong with that code? It should say what? Delete. I got a memory leak. Delete bracket TMP, because I want to delete the whole buffer, right? Okay, and then I return ANS. What's ANS? Well, ANS is just the polynomial, and that's what I return here. So you can see it's even more complicated than the derivative, for sure. Take a lot of time to do it right. So, but just to show you how something like that could be done. It's a display method. This is just an example of how it's running. Oh, this is hard to see. Okay. I'm going to have to look at what the heck that is. That's got to be wrong. That tells me, yes, it's red. Bad method. Okay. Still we have a problem with the red. So here we have, let's take a look why this top one is a bad method. Okay? So notice, anybody, you look at it, you tell me why you think it's a bad method. You are so smart, you can give me a great answer. Yes?
What's in place of the blank? I mean, the blacked out part.
Oh, it just says a bad method.
Oh.
In pointer bad method, yeah. Who can tell me what is so bad about the bad method that we couldn't even show it to you? It's so shameful. Okay. What are we returning? The address of y. What type is y? What type is address of y? Int pointer. Which means it's okay, right? But what type of a variable is y? No? Give me a modifier for it. It's an int. Local, also known as four-letter word, starts with A. Auto. So that means y is created on block entry and y is eliminated at block exit. Where is y actually allocated? Where is y actually allocated?
In parentheses.
On a stack frame. The stack frame associated with bad method. What happens when we return from this method? We go back to the previous one. Okay, and somebody now has a pointer into a frame that's just been deallocated, and they're happy about that pointer, and then somebody else calls another method, which rewrites this area of memory, and that y gets corrupted immediately by another method that gets stacked on top of it. So we return a piece of memory that was never ours. It was temporarily, it was only automatic, right? So this is bad. Very, very bad. Now here, P is an int pointer, okay, and P is equal to new int. So we're allocating P to point at what? At a piece of memory that's allocated from the heap, and so therefore that's not related to automatic deallocation. So therefore when I return P, I'm returning an address to my calling function that's out in the heap, no problem. So this is good. Okay, now we're going to get into fun stuff. Now we're going to get into professional C++ stuff. This is the stuff you can put on your t-shirt and say, if you can figure this out, let's talk. All right, let's take a look at this very carefully. So I have a very simple method called average, which takes two int values and returns an int. And what it does is basically adds those two ints together divided by 2 and gives you the integer division of those two. Okay? What I want you to do what I'm going to do is I'm going to cover this up with my hand, which makes it invisible. I have that power. It's invisible. You can't read it. Okay, now so therefore, we'll call this H, which stands for hand, H. So I would say that H is a header for a function that takes two ints and returns an int, wouldn't you? Right? So this is a prototype because it's not defined, it's just a declaration. It's a declaration of a function H that takes two ints and returns an int. Correct? So that means that star fn is a declaration of a function that takes two ints and returns an int. Star fn is a declaration of a function that takes two ints and returns an int. That means fn has to be dereferenced in order to be a function prototype. That means that fn must be a pointer to a function that takes two ints and returns an int. So we have the notion of a functional pointer. A functional pointer. What's a functional pointer? Well, what's a pointer? A pointer is an address. So if we have int k, ampersand k is the address of the int. The type of it is int pointer, and the value is the address of the k. Well, just like data has to be stored in memory, so it has an address, code also has to be at an address. So it has an address. So therefore, if you look very carefully here, what is fn? Fn is a pointer to a function that takes two ints and returns an int. Average is an actual function that fits that profile, two ints in, int out. So what I'm going to do is I can assign into fn, which is just a pointer, the address of the function, average. Notice that I'm not using parentheses around average. If I use parentheses, I'm calling the function. If I use the function name only with an ampersand in front of it, it's the address of the function. What type is ampersand average? Okay, that is a pointer to a function that takes two ints and returns an int. Average is a constant pointer to that code. But fn is a variable pointer to such codes, meaning that if there was another function that took two ints and returned an int, I could assign the address of that also into fn, and fn would be pointing a different code. So, once I assign fn to point at the same code as average, I can then dereference fn, and since fn is a functional pointer, star fn is a function. So now I'm calling a function that fn is pointing at with the values of 8 and 16, and the result gets a value of 12. Because it just adds 8 and 16 gets 24, divides them and gets 12. It gets worse. And the reason it gets worse is because not only can I do that, I can also do that in C++. It means if you have a functional pointer, you can dereference it to call the function that it's pointing to. Or you don't have to dereference it. It's still going to call the function it's pointing to. So functional pointers are a little tricky because C++ allows flexibility on functional pointers. Don't have to dereference them. In fact, you can say fn equals ampersand average, or you can just say fn equals average. C++ knows if you're not using the parentheses, if you're just using the functional name, it knows you're using the address. So if it makes you feel better to put an address, by all means put an address there. And if it makes you feel better to dereference the functional pointer, by all means dereference the functional pointer. But be aware, you don't have to use this, and you don't have to use this, and it still works. So that's kind of bad, but it's kind of good. So that's, we don't have a lot of flexibility. So you can see over here, same as this one. Let's just look at one more slide right now. So now, let's take a look over here. So now, notice I'm simply reiterating the average function. Two ints returns an int, does something. Sum of squares is a different function, but it has the same prototype. Two ints in and int out. And now I have a function called mystery. Ooh, mystery. Very, very exciting. The mystery function, how many parameters does the mystery function take? Well, I have 3 distinct yellow highlights. Thank goodness yellow is working on that projector. Mystery takes an int, which we formerly called A, another int B, and then it's got this crazy thing that we've seen before. But we've seen it before, so we're not going to panic, because we're going to just read it to ourselves. Star fn is a function that takes 2 ints and returns an int, so fn is a pointer to a function that takes 2 ints and returns an int. So fn is basically a pointer to functions. So it takes an int, and a pointer to functions that have this signature. And then, what does mystery do? Mystery calls the function. So mystery is a function which calls a function it doesn't really know what it is, calls it passing in the parameters a and b. So when we look at the main method here, you see here we say cout mystery 412 average. Notice no ampersand, but I am using the name of the function without parentheses, and that means pointer. So what type is average? It's a pointer to functions with this signature. What's sum of squares? It's a pointer to functions with the same signature. So therefore, these two are very good type matches for fn. So once the functional pointer goes in, we can then, so at this point on this call, mystery calls average, and it prints out 12, but when it sends this one, it's going to give you 144 plus 16, whatever the heck that is. 160? Oh, it says right there, okay. I didn't have to do it in my head, I just did. Okay, so it prints 160. So that's a functional pointer. So we're able to get a function to perform something. We can actually toss in some logic into the function. And we'll be able to use this for some pretty cool stuff. All right, any questions about that? We'll start with that next time. It's a good place to start. Okay, everybody good?